So just like for less pain, right? So let's just plug in numbers. So parts, like the next part might just ask like find the rate constant. Well, if you want to find the rate constant, then it's just going to be rate of trial 1, so 2 molarities per second equals K, which we're solving for. Concentration of A, which is 10, times concentration of B, which is 800 squared. Sorry, and then it's going to be, the units are molarity for each one, right? So then this is going to be K equals 2.0 times 10 to the negative fifth, right? And then the hardest part here is figure out the units, right? Because if you remember, 0 order is molecularies per second for K, first order is per second, second order is second molarity inverse, second inverse. This one is third order, because that's overall, so it's a little tricky. But if you want to keep track, notice on this side is molecularities per second, so M over S. Well, this one has 1, 2, 3 moleculars per second. So if I divide by this, I divide on this side, right? So then this cancels, this turns into a 2. So it's actually molarity, negative 2, molarity to the negative 2, second to the negative 1. Remember the trend I told you, as you keep going down in orders of reactions, you keep dividing by a molarity. It's the same idea. But you can calculate it if you just follow the units. The important thing is just write down the units. Okay. Okay, and then he might ask you like predict the initial rate for for trial 5, right? So you're given all these, right? And he may ask you to calculate the rate of trial 5 because you don't have that. Well, I have concentration of A, I have concentration of B. I don't need concentration of C because like it's not in the rate law. And I'm like, okay, what's my K? Well, I just calculated my K. The K is the same for everything. It doesn't change no matter what. Okay, remember, if I change the concentration, doesn't change it and all that, right? So maybe I'll ask you what's the rates for trial 5. So for this one, I'm gonna find the rate equals K, which was 2 times 10 to the negative fifth, molarity negative 2, second negative 1, concentration of A, which is 4.62, concentration of B, which is 0.117. Sorry if it's like going in. But basically, plug in this for A, this for B, and square it, and then times it by the K constant that we just calculated. So that we get rate equals 1.26 times 10 to the negative 6 molarities per second. Rate is always like some molarity per second. Make sense? Any questions on this?
When you found K, what did you plug in for the rate again?
When I found K, so I just picked trial 1. So I'm like, for trial 1, I'm like, the rate is 2, concentration of A is 10, concentration of B is 100. Right, so I just went 2, 10, 100, and I calculated K. If I did this one, this would have been 20 times 100 squared, that equals like, times K equals 4, right? So if I did any of them, it would have worked. The only one I couldn't do is this one, just because I don't have this information. But once I get the K, I can calculate this, which I found out is 1.26 times 10 to the negative 6. From this. Make sense? Okay. Now, sorry. Okay, so let's say I do let's say I give you this equation, or this, I say, well, sorry, 2a plus b yields c, and then this is c plus d yields e. So if I tell you that so we're gonna do two parts to this, okay? So if I told you that a scientist found out that the following steps are the actual steps of the mechanism, right? Like when he did some research, he found out this is what's actually happening, okay? And then the question is the mechanism consistent with the so this is what we calculated experimentally, and this is our experimental rate law. It's a rate law we got due to numbers we extracted, right? Now, is the experimental rate law consistent with this mechanism, okay? And so what you have to do there is you always care about the slow step, okay? Just like if you're in like a track race, right? And which one do you notice more? The slow person that's running and slacking, or like the fast people competing with the other fast people, right? If someone's really slow, you're gonna notice a lot more than someone's really fast, okay? At least that's the expression I'm just gonna give you guys, okay? So basically we care about the slow person determines the rate of the race, okay? So basically what I'm trying to get out of it, the slow step is the rate determining step. That's what you care about, right? And your rate law should reflect the slow step. Does that make sense? So that means, remember how I said the coefficients, right? Should be the orders, right? So if I ask you that, is this consistent with the experimental rate law? First of all, the answer to this would be no, right? Because if this was consistent, it would have been, the rate law should have been rate equals K, C, D. Does that make sense? And that would have been right, right? Does that make sense? Now let's say I flipped it around and I said this is the slow step and this is the fast step. It's like the part 2 of it. So if I told you that, and I said, is this is this mechanism consistent with the experimental rate law? What would you say? Yeah, right? 2A, wait, well, sorry. This one. There you go. Yeah. 2A plus 2B yields C. It'll be yes, because A is, there's coefficient is 1, so then A is to the first, right? It's first order, right? Coefficient B is 2, B is to the second order. Does that make sense? Yeah? Okay, and then if you want the proper wording for it, it'll be like, is it consistent? Yes, it is consistent with the experimental rate law because the rate law reflects the slowest step of the mechanism. That's like the proper wording, I guess, if you want to think of it like that.
Can you repeat that? Because
Yeah. So, yes, the mechanism is consistent with the experimental rate law because the experimental rate law reflects the slowest step, or is consistent with the slowest step or the rate determining step. Either one, if you say rate determining, you know it's the slow step.
Wait, how'd you find out which one's the one that comes fast?
That's given to you. It'll be he will tell you this. Is this consistent with what you just solved for?
Okay.
Yeah. You won't have to come up with that.
Okay.
Yeah. Or if you said, if the experimental rate law was determined to if the experimental rate law was correctly identified, that is what we know. Draw the mechanism for the slow step. You know that would be A plus 2B yields some product. So you can go the other way, but most of the time it's this way.
Okay.
Yeah. Okay, questions on that? Big star for that problem, because that one's super important. Okay? So let's do okay, so can I erase this?
12 minutes.
Okay. Okay. So now let's dive into some graphs. Okay. So let's say we have this. This is called a reaction profile. So if this is a reaction profile, progress of the reaction. And then this, you can just say energy. If it says potential energy, Gibbs free energy, or just energy, is all the same thing. This could be progress of the reaction, time, reaction coordinate. There's just different names for it. But basically, it's like some sort of time, like how, like throughout the time of the reaction, and then you're monitoring the energy, right? So then I'm gonna give you a graph, and the graph looks like this. Okay. So then I'm saying A, B, C. Yeah. So again, this is also like Gibbs. Okay. So he might be given this, and he'll ask you like a bunch of questions on this stuff. Okay. So, for example, so this is like the beginning of the reaction. This is the end of the reaction, right? What is my reactant? A, right? That's what I start with. What is my product? C, right? What is my intermediate? I'll talk about intermediate in a second. It's actually B. What an intermediate is something that it's in the process but doesn't end up in the overall reaction. So if I ask you how many steps is this? So you guys have probably seen a graph that looks like this, right? That's a one-step reaction, right? Every peak is a step, right? So this is a one-step reaction. How many steps is this? 2 steps, right? So the 2 steps are, so you're gonna learn, especially like biochem and like Chem 14C and D, not everything happens in like 1 step, right? It's like unheard of. There's like 10, 12 different like steps. This does this, this does this, forms this intermediate, blah, 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 right? So like, it's really important to like you're gonna, this is like the most basic view. Once you get to biochem, like, okay, this like citric acid cycle, that's like 8 steps. Does that make sense? So the idea is that the first step is A to B, right? Like this is the first step, right? Second step is B to C. Overall, I go from A to C, and notice B doesn't end up in the overall reaction, right? It's there, it occurs, you'll have a, like, it'll show up, but it's not in the overall reaction. Like, for example, like cellular respiration. If I ask you what's the reaction for cellular respiration, right? Glucose plus oxygen, like C6H12O6 plus 6O2, yields CO2 and 6H2O, right? But that's like the overall equation. They don't tell you about fumarate, succinate, oxalase, like all the other intermediates that are involved in it. Does that make sense? So that's like an example of it. So let's see. So that's intermediate. So B is like in the middle, so that's an intermediate. These little peaks, what happens here is called the transition state. So I'm just going to say TS1 and TS2, just to say like transition state 1 and transition state 2, the second step, right? And the transition state is like something, like for example, if I had, kind of irrelevant to this, but if I had A plus B yields AB, right? So they were detached and then they were together, right? A and B, at this point, they're completely separate, right? At this point, it's like A connected to B, right? During the middle is what's called the transition state, where there's what's called a partial bond between A and B. So it's like forming, not completely formed, not completely not there, it's there. And that's called a